Hi, in this video, we want to take a look at the t-distribution. All right, so it's named after the pseudonym that the statistician who first really explored it. It's called Student's t-distribution. He was supposed to be doing work at the Guinness factory and decided to do some statistics instead. And when he published his work, he was scared about getting in trouble, so he published under the name Student. So it's called Student's t-distribution. All right, so when do we use this? Well, we use Student's t-distribution whenever we're interested in the normal distribution, but we don't know the variance. Okay, so we're in the situation, I want to infer something with normal distribution. Usually, I want to make an inference on the population mean. All right, so I collect some data that is from a normal random variable, and then what I'm going to do, let's say I'm going to do a hypothesis test on the population mean. Well, I don't know the variance, so I'm going to estimate it using, the sample variance. All right, very reasonable thing to do, but there's a catch with this, is that sample variance, from our perspective, that's another variable. Okay, well, that means that's inducing some more randomness into what's going on. Therefore, the distribution is not actually the same as the normal distribution. With normal distribution, I need to know what the variance is to be able to achieve this. Okay, so basically the t-distribution is just one step off, accounting for that additional source of variation in the system. Okay, so let's say that I have independent, identically distributed normal random variables, and we have mu and sigma squared as the mean and variance of the population. We're going to say that t is equal to y bar, the sample average, minus mu divided by s divided by the square root of n. Okay, well, under this situation, this t has this distribution. Now, you'll notice in here that I've got n's floating around. All right, so these n minus 1s are equal to the degrees of freedom. Okay, so here, this is a distribution from this sample. Okay, well, this looks kind of ugly, right? I've got a gamma function in here. I've got square root of pi and n minus 1, another gamma function, and then I've got, a fraction inside here. There's a lot going on. This is a pretty ugly distribution if you're going to be working things out by hand. Fortunately, computers take care of it for us. All right, so now let's compare it to the normal. Okay, well, here, if I take a z and set it equal to y bar minus mu divided by sigma over the square root of n, so realize that this is the variance, this is the standard deviation of y bar. Okay, so I take the standard deviation of the regular y's, and then I divide by the square root of n if I'm taking a look at the sample mean. Okay. Well, this is going to be standard normal. Now let's take a look at the two distributions. So here's some R code just to get a visualization for us. And here we can see that the red is the density of standard normal, and the blue is the density of the t-distribution with 1 degree of freedom. Okay, that's a sample of 2. So I've got a sample average of 2. All right, well, you can see that both of them are centered at 0. We can see that they both have just one peak. You'll notice that there's a lot more in the middle. The red is higher, and to the side, the red is lower. All right, so more of the mass of the normal distribution is towards the center, while the t, more of the mass of the density is farther out, away from 0. So what's going on is that if I'm working with a t distribution with 1 degree of freedom, I'm going to see a lot more extreme observations farther out from 0 than I will with standard normal. Okay, so the t distribution has heavier tails than standard normal. All right, now let's take a look at the expected value and variance of the t distribution. Okay, there's a catch on this one, just a tiny little catch. All right, it ends up that the expected value and the variance aren't always defined. Like what? Like or so far in my videos, we haven't talked about anything like this. All right, so it works out that if I was to take the integral from negative infinity to positive infinity of the blue curve, there's so much mass far out that the integral is not defined. The calculus doesn't work out. Okay, so if n is greater than 2, then the expected value is 0. But if n is equal to 1 or 2, then there is no expected value because the mass is so spread out. Now, if n is greater than 3, the variance is this fraction, and you'll notice that this fraction goes to 1 as n goes to infinity. Now, if n is 1, 2, or 3, this doesn't work out. We don't have, like, this is not defined. So notice that the expected value is the same for t-distribution or normal distribution, and they're both symmetric, and they both have a peak in the middle. But the variances are pretty different. The variance of t-distribution will always be greater than standard normal, no matter what happens. But this fraction goes to 1 as n goes to infinity. So if I have a really big value of n, this is so close to 1 that I might as well just call it 1. All right, let's take a look at some special cases of the t-distribution. Let's look at n equals 2. So here I have 1 degree of freedom. All right, so the expected value is undefined, and we have infinite variance. All right, this is called the Cauchy distribution, and this is a common distribution to use in modeling and simulation because it can give us extreme values that we weren't expecting when we were preparing our simulation, when we're doing like bug hunting and stuff like that. All right, so the cumulative distribution function involves arctangent, and it's just 1/2 plus 1 over pi arctangent. And here is the density. And if you remember from Calc 2, this connects directly to arctangent very nicely. Now, if we put n equals 2, oh, sorry, this is, yeah, n equals 2. Here's the density. So this is pretty heavy, tails. Now, if n is equal to 3, now we have an expected value. It's 0, but the variance is still infinite. And here is the distribution, and here's the cumulative distribution. So we still have these beautiful fractions going on. Notice that the gamma functions simplify out for us, though. And here it looks a little bit more like a bell curve or standard normal, but it's still got heavier tails. Now, if n is equal to 4, then we have an expected value and we have a variance. Now the variance is 3. This is much larger than standard normal. Standard normal always has a variance of 1. So this is 3 times as big. All right, well, if I go through and do the calculations, here is the density, and here is the cumulative distribution function. All right, so now let's take a look at how it compares. All right. So it looks a little bit more like standard normal, but it's still got a lower peak in the middle and heavier tails. Now, what happens as n goes to infinity? Well, as n goes to infinity, if I have a really big sample size, then the t-distribution looks a lot like the normal distribution. In fact, the t-distribution converges in distribution to standard normal. All right, so let's take a look. Okay, so what's going on here is that the dark line here is standard normal. Now, the remaining lines are t-distributions. The darker ones are lower degrees of freedom. The lighter ones are greater degrees of freedom. So you can see that here we've got degrees of freedom 1, degree of freedom 2, 3, 4, 5, 6, and so on. Now, I colored it to get lighter as we get greater. And you can see that when we get into the yellow, it looks really close to standard normal. It never actually reaches it, but it gets super close. Here there are 30 t-distributions in this plot. So you can see by the time we have 30 degrees of freedom, which is 31 observations, then it's so close to normal we can just say, hey, we just call it normal. Now, my opinion is that if you're using a computer, you really should just use the t-distribution functions and not worry about the normal distribution itself, just because it's a more precise representation. There's really no loss, but a lot of people talk about, like, once you get greater than 30, you just go with normal distribution, which is, standard practice. All right, that's all I've got for you. Take care and goodbye.